Okay, all right. Hello, everybody, and welcome back to BCH Bliss Day 3. Welcome back to our live stream viewers, of course. Today is the upgrade day, 1 year of work or more from the BCH community for the Velma upgrade, which we will be celebrating later today and this afternoon, local time. BCH Bank Run is on, so feel free to tweet about that, make noise on social media, jump on any exchange and withdraw some BCH so we can stress test their reserves as we've been doing on the 1st and 15th of every month. And a couple of people asked me, look, Jeremy, I don't have much or any fiat, how can I contribute? And well, of course, you can make noise on social media, but any way that you acquire non-custodial BCH will have the same effect by the invisible hand of the market. So if you are in that situation, try and send someone an invoice or acquire some BCH by trading some goods and services on that day, because it doesn't matter whether it comes from exchange, just as long as your non-custodial stack is going up, it's adding that pressure onto the exchange reserves. Okay, we also have the raffle tickets. We'll be drawing that later today with the upgrade. You can still talk to Barbara if you want to grab some extra tickets. At 6 p.m. today, we will be having a Fifth of Gaming Street Fighter tournament. Jonathan asked me to remind you all to go on to fifthofgaming.com and sign up. You can't really kind of sign up once it's already going. AFOG doesn't mess around, so sign up early if you want to be on that. Our sponsors, we have to thank again Mike Komaranski, the Bitcoin Cash Podcast, Commercial Kitchen Stop, Ravish Off Ocean, BCH Bull, Mini Satoshi, Molecular Turek, Steve Thurmond, and Bliss 2024. Okay, now we have the talk you have all been waiting for. The man behind the VM limits upgrade implementation himself from BCHN and Fulcrum, representing the United States of America. Calin Culianu.
Hello, everybody. Thank you.
And here's
All right. So today I'm going to be talking about virtual machine upgrades, the ones that are upgrading today, and potentially upgrades that are proposed next year. A lot of this work, or all of it actually, is Jason Dresner's very hard work in research and in thought and in chips. So I'd like to thank him. I'm basically presenting his work, but I implemented it, so I know a lot about it as well. If he could be here, this likely would be his talk. But I'd like to thank him very much because he put a lot of hard work, and he's a tremendous asset to the Bitcoin Cash ecosystem. So we're lucky. He's got tons of years of experience thinking about these things, and he does research, and he's awesome. So the upgrades that are going to be activating today, they're virtual machine oriented, both of them. There are two major, there's the VM limits and there's arbitrary precision integers, or BigInt. Not to be confused with the other BigInt. We had another BigInt, but that was 64-bit integers. This is going to be 80,000-bit integers for now. It's going to be you can hopefully do any kind of math you want with that many bits. I mean, it's more than the particles in many universes, probably. Yes, so the VM limits, we more precisely and specify and constrain the virtual machine execution than what status quo, than before the upgrade. And this expands the integer arithmetic to ridiculous levels. So you can hopefully do anything, including like cryptography or whatever you'd want to do. And then these are the upgrades that are in discussion now for next year, and they're also virtual machine oriented. The first one that was proposed is pay-to-script. Many people are familiar with pay-to-script hash or pay-to-private key hash. This one is just sort of, it almost seems like strange because you no longer are going to be having these templates for what's allowed. You can actually pay to any script, like any code, but only up to 201 bytes. And there are two other things included in this chip. It's the C script, the script sig, the script sig, the unlocking script can be, right now the limit is 1650, it's raised to 10 kilobytes. And the token commitments, the NFT commitments, now they're 40 bytes, they're going to be raised to 128 bytes. Another proposal is loops, and this leverages the VM limits that's activating today. This would leverage it to allow for looping in code. So you no longer have to do you can kind of do loops now by just unrolling the loop you want and having a whole bunch of if statements. And this would just allow for actual loops, and they're constrained by the virtual machine limits that are activating today. Another proposal that's coming is the function evaluation of some sort, so you can do code reuse. You can scripts that are doing repetitive tasks can be compressed. You just call into a function rather than copy paste the same boilerplate. Right, so let's take a step back. The virtual machine. What is a virtual machine? It is the execution environment for Bitcoin script, which is a Forth-like programming language used by Bitcoin Cash to decide if a spend is valid or invalid, and is the basis for creating rules regarding any transfer of ownership or a spend. But since it's a programming language, you want to be careful. Programming languages can potentially never halt. So one of the things that's really easy in programming language design is if you create a language that can't loop in any way, you're guaranteed it halts. So it has some limit, right? Sort of in computer science lingo, if you just say no loops, people understand what that means. And sort of Satoshi, this is taken from the original Bitcoin sources off of that Nakamoto Institute site. This is actually the eval script function, and he has a comment here. He's like, script is a stack machine like Forth that evaluates a predicate, returning a bool indicating valid or not. There are no loops. And so this statement has sort of been remembered as just a quintessential aspect of Bitcoin, right? We have a language, but there are no loops. And sort of it's repeated often. And it sort of feels kind of strange that one of the proposals is about loops, like we add loops. It's like we're violating a predicate. It's like we're violating the prime directive, like Star Trek or something. And so, but, the reason, I'll get into why, there are no loops is shorthand for something. It's shorthand for this is not a Turing complete language. It can't loop. It halts. So yes, the significance of no loops. So when talking about computer languages, there are at least two general classes, perhaps more, but the two major ones that most people think about when they're talking about computer languages are Turing machines and deterministic finite state automata. So an example of a Turing machine would be just about any programming language that you've seen that's Turing complete, which is most of the ones people use, like JavaScript, Java, C, C++, like anything you would think of using that has loops in it and that has all the structures you expect. And you can actually model any computing problem. You have loops and looping mechanism, but it has this thing called the halting problem, which is an unsolved problem in computer science. You cannot prove that like all Turing complete languages halt. Like a program you would write in that language may not halt. Like there's no way to know if it finishes or not. And DFAs are the other class, which is, I would say, the existing Bitcoin script is in this class. They're generally like an example of a DFA that most programmers have seen is a regular expression. It doesn't, like a normal regular expression, they're advanced ones. But a normal one, it doesn't halt. It's used for text processing. It's basically doing a transformation, following some rules. And so Bitcoin script is more in this class. So when you see no loops, right, that's like the easiest shorthand to ensure that you're kind of in this category of languages. And that's why Satoshi chose that, probably because he didn't have a lot of time to think about, or we're guessing, to think about like how he would do a more robust language. And at the time it seemed great. It was like a step beyond anything. So. Right, so initially, which is strange, this is Jason's old research which I'm presenting. When thinking about how to liberalize the virtual machine to be more capable, he had to go back and do some historical analysis, like what were Satoshi's design decisions in a lot of the constants we see. And it turns out he came up with ad hoc limits. Because early in Bitcoin's history, like right after the release, like the first source code you can download, there are like no real limits that we think of now. The only limit was no loops, and so like the stuff that came out later was sort of an improvisation, like ad hoc limits, because right after Bitcoin's release, it became clear that poison blocks could be created that take like forever to validate. And so he sort of improvised like patches, and some of them were stealth patches, to like constrain the virtual machine. Like initially, it had BigInts from the beginning. It had arbitrary precision. It was using the OpenSSL library, and that sort of explains why the number format, the C-script the number format is the way it is. It was like OpenSSL compatible format. But then he had to all constrain that. Went down to 32-bit integers, like opcode limits, like just to avoid the worst possible scripts you could write. So that's sort of the history of it all. Right. So the VM limits, right? So this chip, which we'll activate today, um, it's sort of going to solve the problem it is going to solve the problem of like how to make the Bitcoin script more powerful, but also not like violate like the sort of the constraints we have already in terms of performance. Like, so these are the details of what's going to be activating. The first thing is that the famous and infamous 201 opcode limit, which like I believe even Moria has hits often, like they're really worried about it, and anyone that's doing anything advanced, this one is going to be lifted completely, and it's going to be replaced with a different scheme where you're like every opcode that you encounter has a base cost of 100, and that goes towards counts against you towards some limit that's pre-computed. So these changes will also take into account the particularly high cost of hashing using a hash iterations abstraction, which sort of counts like extra towards your towards your costs. So that because hashing turns out to be one of the more expensive things if you do it abusively, and signature checks as well are very expensive. And so we're also going to be raising the stack data item limit from 520 to 10 kilobytes. And one of the little things is that currently, because of the 201 opcode limit, you can't really do nested ifs deeper than 100. And so in this upgrade, we're just going to preserve that property, since we don't want like nested ifs going to like 20,000 deep or whatever, 5,000 deep. So and a key property of the limits is that they're density based, sort of like the way the sigchecks limits works now. It's all about the size of the script you're evaluating, or the size of the block. And so you know that for any particular size block, you know exactly the worst case of how much execution time it can take. So if you have a 1 megabyte block, you know that the worst case is going to be this. So yeah, it's density based. It sort of keeps in with the current design philosophy of Bitcoin Cash. And these are just some details. 800 op costs allowed per script byte, 0.5 hash digest iterations per byte, and a hash digest iteration is like, depending on the hash algorithm, like how many iterations it does. Yeah. So the old limits had some limitations. The 201 opcode limit was too restrictive, as has been talked about. And so more advanced contracts definitely would hit this and then have to optimize. And some things weren't even possible in just one script, like you'd have to chain them or something. But so like raising the opcode limit could introduce the possibility of some abusive things that you could imagine, like a large data push, repeat this like a bunch of times, and then op2 hash 160 up, right? Just keep doing this, So if you just if that's the only thing you do is raise the opcode limit, you're going to have problems. So that's why we needed to come up with this, this more comprehensive sort of scheme, which costs limits in a different way, a different philosophy, not just opcode limit. Yeah, but the opcode limit penalized legitimate scripts in defense of preventing excessively abusive ones from executing for too long. Yeah, and so these numbers that we came up with are sort of, or that Jason mostly came up with, I should say, are like just to identify the worst offenders in script execution and constrain them, and then still allow like the good stuff to happen. Yeah, and so liberalizing, that's another key feature of this upgrade, is that from 520 byte data pushes, you can get 10 kilobytes, which sounds, whoa, you're going so fast, that's so much. But it turns out just pushing data like to the stack, like that's just like you're copying bytes around. Like computers do this so quickly, it's like, it's irrelevant compared to like hashing or other stuff that's super slow. And so that's just costed proportionally to the size of the data you're pushing. Yeah, the pushing data to the stack is not a huge deal. Shouldn't be free, obviously, but it needs to go into the scripting cost, but it's like weighted, it's balanced, Yeah, we've correctly accounted for the hashing and using this other scheme with hash iterations. So why not? Because one of the reasons why this data push limit was the way it was is probably to avoid excessive hashing. We're guessing that's one of the, because Satoshi never really described why he made the decisions he did, but you can kind of guess. And so yeah, now that we've correctly accounted for hashing, like why not liberalize it to 10 kilobytes? And it aligns with max script size, which that's been preserved. The largest script you can evaluate is 10 kilobytes. So yeah, you can get, if you think about the stack, and then the stack has 1,000 item limit, you can get about 10 megabytes of scratch space per script to work on, and that's perfectly within alignment of anything you'd want to do. Like in computing now, it's like not, it's not too generous. In fact, it's a little bit stingy, and it's fine. Yeah, it's not a lot of memory to allocate per core with modern computers. And these are just some details. These are just taken from the chip in case you want to see like a bullet point list of like each of the things that that was altered by the chip for VM limits. I'm not going to go over each line of these because it's just a lot of code stuff, but yeah, I mean, here's like one of the examples of signing is like very 26,000. You know, it's like really, really penalized as opposed to something like pushing is proportional. Does it say that? Like pushing is proportional to just the size of the data. So if you're pushing 10 kilobytes, it's 10,000. Which is like half of this. And it's yeah, everything is sort of weighted. And in like stuff like multiplication. It gets like an extra quadratic component to its cost because if you imagine if you're using like a BigInt library, it's got to do like a, n times m or whatever, potentially examinations of the data. So you just weigh that in, and it's still fine. So if you're multiplying two huge numbers, you're probably going to hit the limit easily. Yeah. But the limit is proportional to the script size, so just make your script bigger, and maybe you can you can get away with it. This is just an example of the C code for like how we calculate the limit for like a particular script, just in case you wanted to see it. It's a very simple expression, right? It's basically proportional to the unlocking bytecode length times the constant. So here's an example. Like if you wanted to really iterate in your head, low-level fourth code of like how the limits end up accumulating as you go through. This is a 30-byte script. So using that expression from before, you get a 56,800 limit for this like tiny script, which is pretty cool. Like you can do a lot. And then this script is just doing some trivial stuff. It's like pushing two words, it's concatenating them, it's reversing a different word, and then it's comparing if they're equal, and then the equal comparison is pretty trivial. Whereas like concatenation is it's like proportional to the size, like because this is just like simple manipulation of data, and you end up with this script 846, and you're well within. But if you were to do sig checks here on a script, roughly the size or maybe bigger, you'd end up like easily, if you do too many, because of the 26,000 for 6 checks, you could end up busting this. But of course, with sig checks, you end up with larger scripts anyway, so the limit will be bigger. So yeah, this is an example of hash. This is just to illustrate how hashing ends up like growing. This is still a 30-byte script, but this one ended up costing 846, and this one is doing something very similar, except at the end it decides to hash rather than oops. Here at the end it was adding. Here at the end it decides to hash, and that hash ends up being weighted more. Like this particular operation, incremented at like 300 or whatever, or 400 actually. So yeah, hashing is a little more expensive, and so that if you end up doing scripts that abusively hash a lot of data, this grows quickly, and you can hit bust the limit. So we sort of constrain hashing. So yeah, this is another example of a sig check script where this is more typical of something that's checking signature is going to be about this size. So you get like a pretty big limit, 275,000, and you have a hash iteration limit. So you do it, and then you end up with a single sig check is going to be on the order of 26,000 plus some little details. So if you're just like looping and sig checking or whatever, then this starts to bust out. You can't do too many sig checks. You could probably do about 10 on a 303-byte script. Yeah, so the summary of the VM limits upgrade, which is activating today, is that its costing is relatively low for fast operations. Slow operations like signature checks and hashing have higher costs, with signature checks being the most expensive and hashing cheaper, but still not as trivial as like just normal data manipulation. So in this way, we prevent abuse. And script with fast ops that are just doing trivial manipulations of data or logic, you can totally get like thousands of opcodes now, and like it's not a problem. So the 201 thing is gone, and yeah, so we allow scripts with fast ops, like, and we correctly penalize the slower stuff, and But one interesting property of this, because we're costing as we execute, and we solve the halting problem, right? So this can kind of pave the way for future expansion, which is something I'll talk about later, which is loops. The other upgrade that's activating today is the high precision integers. The original Bitcoin used big nums, and it was later reduced to 32 bits due to bugs and DOS concerns. And just to say, like, some crypto apps may need larger than 64-bit, which is the current limit. So we want to just have arithmetic be something you can do, like, for whatever you want to do, even if you want to do cryptography and 496-bit, 4096-bit RSA keys, like whatever you want to do. We want that to be possible to do in Bitcoin Cash in the scripting language. So yeah, we've already upgraded from 32 to 64 in 2022, but that was not enough. It turns out going beyond 64 bits, it requires emulation because the machine can't natively do that normally. So you need to use like a library, but you also need to accurately cost it. You can't just assume that it's like a single clock cycle doing it. You have to sort of take into account the amount of data you're multiplying or whatever. So yeah, the VM limits chip gives us the accurate costing, so then we can benefit from that, and why not just activate arbitrary precision integers now? Since we have accurate costing, we can get away with it. Yeah, arithmetic ops are cost proportionally to the number of bytes they manipulate. Yeah, so this is just a bullet point list. Like all the BigInt changes are the 8-byte integer size, which is really 64 bits, is completely removed. It just ends up being whatever can fit on the stack, which is currently 10 kilobytes as of today. So yeah, 80,000-bit integers. And the arithmetic ops are costed taking into account the byte size of the data and the complexity of the operation, so multiplication is costed much higher than addition. Implementations are encouraged to use the fast BigNum library, and BCHN uses a recent version of libgmp, which is very mature and highly optimized and well tested. So I was sort of going to go into some C++ specifics of, like, we try not to penalize stuff that's not using BigInts before activation. Like, we have this class that's like just the old implementation, and this is sort of just for C++. I'm not sure if I should go over this in detail. I'm going to leave this slide up so you can look at it. But the idea is, like, we wanted pre-upgrade. We didn't want code to pay for what it didn't use until the upgrade activates, and then we end up switching to this bigger class. Yeah, this is something sort of, this is kind of cool that when implementing it, I discovered that, like, the OpenSSL BigNum library, like the binary format of the numbers is the same as the C-script number format, which is the same as what libgmp expects when you're importing, which is kind of cool because then you can very quickly import and export data from the library to the stack of the virtual machine without having to, like, convert all the data. So it's, like, really fast. Like, you can operate on a lot of data. And so yeah, it's just one call. And PZ import, just take my data, suck it up, slurp it up, and I was kind of cool when I was implementing it. I thought that was pretty awesome. And it turns out to really matter. Like, if this were slow, it would just constrain the speed of, like, math ops. Because importing and exporting ends up being, like, the slower part if this part is slow than the actual, like, addition and multiplication you're doing. Yeah, so the summary for BigInt. Integers can exceed the current 64-bit limit. The limit is just really the data push size limit. So if you end up with an intermediate value that's larger, that ends up on the stack, that your script's going to fail. That's larger than 10 kilobytes, but otherwise, it'll succeed. Binary encoding is the same as the current. So there's just the C script. Then the script numbers can just be bigger now than 8 bytes. You don't have to worry if you're not really worried. There's nothing you really have to do. And yeah, the BigInt one leverages VM limits to disallow abuse. And yeah, so one of the nice things is some contracts that really needed larger math probably had to do a lot of intermediate steps, like very big contracts, and now you could just do it as, like, one opcode, like add or whatever, multiply. You don't have to worry about overflow necessarily, so that's nice. Right, so yeah, so these two are the ones that are going to activate. So the BigInt and the other one, the VM limits, are going to activate today. And now I'm going to go into what's been proposed for 2026. one of them is the pay to script that I mentioned. And so currently for relay rules, which is standard scripts, basically fall into one of like these 5 templates. So like if it doesn't look like this, it's not going to be relayable, and likely you can't get it mined unless you like do it from a side channel to a miner. And this is one of the reason for these templates was, as I mentioned before, like you wanted to sort of constrain what ends up in the UTXO set and also the complexity of these scripts. So yeah, there's like 5 different templates. It's the P2PKH, pay to pub key hash, which is most Bitcoin addresses that you see are this. Some Bitcoin addresses you see are this. They end up mapping to these templates. Then you can do like data carrier, op return. And then this one is hardly used anymore, but like originally Satoshi was using this in early Bitcoin days, the pay to pub key directly. Is you just have the pub key and then like check sig. And then there's bare multisig, which is still supported. And that's up to 201 bytes. Where you have like a bunch of pub keys and then a bunch of, yeah, this is basically like a pay to script hash, but you can do it without this pay to script hash. You can just have it as an output. And like, so if any transaction like uses a script as an output that isn't one of these, it's not going to be relayable. But with pay to script, we're allowing like anything, like as long as it's under 201 bytes. So it doesn't have to be just one of these. And the choice of 201 bytes, the rationale for it, it's just the same length as bare multisig, the max one you can have. So something like this could be not relayable, which is like just a script that's OP0, nobody can spend. Just a script that's OP1, anybody can spend. A one-time use password protected spend, like you can just do that and have that, hey, send me money here. Or something that like the signature is going to be any like odd number. Like that's something you could just have it as a destination for any Bitcoin, for like a standard transaction, Bitcoin transaction. There's another one that spendable only by a specific token, and etc. I mean, as long as they're under 201 bytes, like anything goes. But why would you want to do this? Like you already have pay to script hash, right? So you can like do any arbitrary script anyway with that extra step of the pay to script hash. And the motivation cited in the chip is that for small contracts, like going through a pay to script hash, like that level of indirection ends up being like, first of all, you're wasting space. And also like it just makes it a little bit harder for the contract author. And but one key thing is like if it is a small contract, there might be a class of contracts you don't want people to easily be able to send money to. Because right now, pay to script hashes, they all map to an address. Like you could have an address, and some user can end up sending money to this contract, like which makes no sense really. So if you wanted a contract that's sort of kind of hidden, that people can't easily send money to, this pay to script, because most wallets are going to be discouraged from offering the ability to send money directly, like from as a user, just like clicking, And so that's one of the other motivations, that having the contracts not be pay to script hash. Might guard against people locking funds in something that doesn't make sense. So the additional changes are like these other 2 bullet points, which are just the script sig or the unlocking bytecode is raised from 1650 to 10 kilobytes. And the motivation for that is that after VM limits, sort of worrying about bytecode of the unlocking is not necessary. So why not just liberalize it? And this would allow for much more complicated pay to script hash contracts. Because right now you only have 1,650 bytes, and now you can have like 10 kilobytes. And yeah, the other thing is it was observed that sort of 40 bytes for the NFT is not enough. Like if you wanted to do some kind of cool stuff, cool things, you really need a lot more. So why not liberalize that? So what are some of the risks? I thought of, when I was preparing the talk, I thought of these 2 things, but I'm sure like over the course of the next year, hopefully people come up with why this is a bad idea or a good idea. Immediately, the 10 kilobyte unlocking script, like it sounds a little bit like the BTC ordinals, except you don't get the discount. Like maybe that's a convenient way to store, like, I don't know, is that good or bad? So, and also the other thing is, if you allow anything as the locking script, like as an output, it ends up in the UTXO set, and like you can like totally bloat the UTXO DB with like 201 bits, 201 byte bits of data, because you can like literally have any script, and this doesn't count towards your op return limit, which is currently 223. Like you can just have like 1,000 or whatever, 1,000 outputs or 500 outputs that are 201 bytes of just like pieces of a giant JPEG or something, and then they're all in even worse, they're all in the UTXODB until they get spent. So it's like doubly bad. So these are two things I thought of that are like, whoa. So because I want, these aren't actually going to activate yet, or they may not, or they may. And I want us thinking about, having a discussion, maybe in Bitcoin Cash research about all these considerations. Yeah, so, okay, now I'm going to the next one that's been proposed. This is the loops. It's pretty straightforward. I mean, you just introduce two opcodes, begin and until. And if the until condition isn't satisfied, you go back to begin until it's satisfied. And these things can nest, but they can't nest in a weird way. Like it has to be like neatly nesting. Like you can't have an if around an until to control the nesting. Like it has to be kind of the way you would do in a normal programming language. Yeah, so the loop construct is added to the scripting language, and it may be nested up to 100 times, just like op-if. The op-if nesting and the loop nesting sort of count to the same limit. Like they both have to together not be 100. And so the original, this is the thing I started to say at the beginning, like the no loops paradigm is violated now. It's like BCH kind of becomes Turing complete, but you have an execution limit forced. So you do know you're going to halt, like eventually, thanks to VM limits. So you can get away with this. You can now allow loops and not worry about the halting problem. And this is an example of some code, like some fourth code of the construct. It's like it does a bunch of stuff. The condition's not satisfied, go back. This particular thing just figures out like how much a number is divisible by 5, which is pretty useless, but it's the only thing I could think of that's pretty easy to fit on a slide. And it keeps looping, and then it's happy, and then like you have the result. And so if you were going to do, I mean, obviously for this is so trivial, like why would you even bother? But if you were going to do something more complicated, where you're sort of trying to like figure out what the pattern is on some piece of data, or how many outputs you have, and like for each one do something, this is much nicer than unrolling this loop and having each iteration of it guarded by an if or something. And obviously this is cleaner. So yeah, loops, you can think of this as a summary. You can think of them as a way to compress long scripts and sort of just jump back to the same code rather than unroll loops. It definitely leverages VM limits to guarantee that looping cannot lead to like breakout scripts that just slow down validation or halt it completely. And it makes BCH script much more expressive and useful and easy to understand, and just everything Turing complete, but with an execution limit. So there's no halting. There's the halting problem. It doesn't exist because you constrained it. Yeah, and so one of the last thing that I want to mention, and this is a bit unclear as to how the mechanics of it will be, and there was some controversy surrounding exactly which one to do, but another thing that would be nice is function evaluation. If you can imagine some really sophisticated script might not neatly fit in the 10 kilobyte limit, so you might want to just call the same code that you're doing, functions what you'd have in a programming language. Like it's sort of another trick to compress scripts, so you can do code reuse. And there are two major things being discussed now as far as how to implement it. One of them is op-eval, which basically any stack data item, you can like call into it as code. And you could keep doing that recursively if you want. And so this is the one Jason has proposed. He has a chip proposed already. It's like well thought out and fleshed out. And it's potentially very flexible and compact. Just the minimum number of opcodes you need, like minimum number of bytes you would need. You can even do cool things like closures with op-eval, because you can take a snippet of code and then bind some variable inside of it. Like you can concatenate and then like execute it. So I don't know if that's interesting for Bitcoin script. Like, do we really need closures? But that's just a curiosity that you can do that. And then code that writes code has benefits and trade-offs. Like the benefit might be if you wanted to really obfuscate some path in your contract, not make it easily analyzable, or something like that, or even emulate P2SH within your script, where like you don't want some spending path known to everybody. because I don't know, some kind of secret thing, then you could do that with op eval because you could totally hide all the code that's going to execute behind a hash or something. So that's kind of cool. But then the trade-off, like the downside of that is like you can't do static analysis anymore in contracts, or you can make contracts that are so difficult to analyze and that have hidden paths, and that could be bad for like transparency. But for like crypto stuff, that could be good if you want to hide some paths. Like I don't know. So these are kind of the trade-offs with op eval. Like it's like a double-edged sword. Like you, and then the other approach would be something like you just declare functions ahead of time, so you know in the script like what the exact code that's going to execute is. Nothing from outside can execute, and then call func, declare func, and no code there, right? And this is harder to obfuscate, so this can be a benefit or a drawback. Op eval, basically, you can just emulate pay to script hash within a script now. With this, you can't. Yeah. So yeah, that's my talk. I went into the weeds a little bit, and I hope that sort of seeing the details of the trees helps you also see the forest. And yeah, that's basically. And so yeah, thank you very much.
All right. Do we have any questions for Calin?
So if you're out of budget for the execution of your script, would the way to solve that be to then just pad your input with arbitrary?
Yeah, so it incentivizes padding if you want to do more. Okay. But so that's like, oh my God, we're bloating the blockchain. But then at the same time, you're paying more fee. There is a block size limit. I mean, there's a transaction size limit, and sort of the currency for Bitcoin has been just the data size, and so this sort of keeps with that. Like if you want more execution time, make it bigger. And then one of the things is that for a block that's 1 megabyte or something, exactly.
Yeah, it's not necessarily a bad thing.
Yeah, it's not, but it does. It does incentivize.
Least, yeah.
It does incentivize padding your contract if it doesn't fit. So, yeah.
Any other questions? Yeah, I've got a couple questions with my with the pay to script stuff.
Yeah.
And the ability to shrink the gap between consensus and relay policy, especially with all the drama we've been seeing in BTC recently. I was wondering if you could elaborate on your thoughts on that a little bit more. Do we want to maybe eventually get to a situation where BCH is just all like relay policy and consensus are all standardized? How much research needs to go into that? What would be the potential trade-offs?
So the person that's thought about this the most deeply is Jason, and he's convinced me that if you have really good VM limits, then the two things don't matter anymore. Like you could actually unify consensus and relay. Because the whole justification for the relay stuff was to constrain like the worst possible things you could do in Bitcoin script. And so, yeah, I mean, one of the popular positions in the Bitcoin cash space is, let's someday just dream about having no difference between what a miner can mine and what a transaction in the mempool. Because that's where all the bugs and surprises and potential DOS lies. Like everyone's thinking about standard transactions, and then some miner makes like an evil block, and we never even thought about it because we're busy in the standard relayable space. So ideally, you'd want there to not be a difference. I think just for the clean design, just to guard against mistakes that humans can make, and so that's sort of the direction I think that Bitcoin Cash is going in. But it remains to be seen if we can do it completely or. Yeah, because if you do end up constraining, so like the blocks that miners can mine are pretty expensive, like in some of them, the worst case. So maybe you'd want to constrain that even more. And then that might theoretically make some stuff that's been locked in a locking script unspendable, but maybe not. So I don't know. That's sort of the discussion surrounding. But that's a good question. Thank you. Yeah, that is something that's on the radar, like unifying relay and consensus.
All right. Any other questions? Oh, one more.
Dagger. Yes.
I'm just wondering, with the new method of calculating costs, if it's still easy to do static analysis of your code. Like before, you could just count opcodes and you could count sig checks.
Yeah. So even opcodes that aren't executed get the fixed cost of 100.
Okay.
But like if you're not going to take one branch, let's say in an if statement, one branch that pushes a bunch of data, you don't get charged for the data that didn't get pushed. So you would still, like, I can imagine with some complicated code, you would still need to simulate it to know that for a particular set of data that the code is running, like what the cost is. I guess you would have to evaluate all the branches that it could possibly take to figure out what the worst case cost is. So, I mean, that's doable in a sufficiently advanced static analysis tool, but just doing it visually can get complicated if you have like a lot of branching, you know, where you end up, you know what I mean? Like you end up with like 1,000 branches potentially or something. I don't know. Probably not that many, but you still would have to simulate it or use an advanced tool. Like for some sufficiently complex scripts, you can't just look at it and know right away what your actual cost will be. If you want to know the worst case, you know it immediately because it's all based on the data size. Like if you want to know what your limit is, I mean, on the script. But yeah.
The worst case is the most interesting one. So
if you're writing a contract that's really complicated and you're worried it might bust the limit, you would have to go like down each branch or something like this, or maybe someone can write a static analysis tool that can do it. That's a good question.
And finally, we have the Velma upgrade obviously going live later today. So could you just explain the median time passed and how we're going to know when does it actually activate, what time, and how does that work?
So the median time passed is like a continuously like increasing value, like it can never go back in time. And so that's gonna, when the median time passed is at UTC 12 o'clock noon today, which is 1 o'clock for us. The upgrade will activate. However, because median time passed, it takes into account like past blocks to like get an average. It's more likely going to be something like 2 hours or an hour after 1 o'clock p.m. today. So sometimes around 2 or 3 p.m. The upgrade will activate, and we have to look at like, because you can get like 20 blocks in a row really quickly if the price goes up like during that time, right? So then that could be like 12:05 or something, or for some reason if the price crashes and hash rate walks away from Bitcoin Cash for a little bit, you get really slow blocks, so it can end up being like midnight tonight, because for the median time passed, you always look at like 6 blocks in the past to derive that value, or actually 12 blocks in the past, but. So the median time passed is like a little bit lagging behind the actual real time. I'd have to show it to you. Like I'm so in the. I feel like I'm sort of creating a word salad here, but median time passed lags behind the current time, and it's a function of how many blocks were mined recently. But so if not a lot of blocks were mined, it could end up being it could take a long time, or it can be really short.
It's 11 or 12 blocks that we're watching for.
So it's like the median of, you take 12 blocks and you take the median time on of that 12. So if you get 12 blocks really quickly and like at 12:01, it's going to be a 12:01. If you don't,
Anyway, it'll be between 2 and 3 this afternoon.
Most likely between 2 and 3. Definitely not at noon, even or at 1. Sorry for the long explanation. You have to see the code. It's confusing.
We'll have like some kind of visual indicator on the screen as well. Okay, that's it then, I guess. Put your hands together for Calin.
Thank you.
That's it.
Thank you, man.
All right, let me just check the time here. It's 10:30, just about 10:25, and according to the schedule, we'll be back at 11. I think we can stick to that. We'll be having the technical panel with myself, Daga, Mathieu, and Callisti. So feel free to go outside. I'm sure there'll be some coffee and drinks and so forth like we've had the other days, and mingle and chat. Prepare yourself to be celebrating Velma, and I'll see you at 11 o'clock.